All right, here we go. Video 2 on the introduction to the normal distribution or the normal curve. We're going to talk about measuring position because what we talked about a minute ago were very conveniently if we were exactly positioned 1 deviation above the average or 2 deviations above the average, etc. That's all fantastic. But what if you didn't land exactly 1 deviation above or below the average? So that is a bit of a problem, and we will talk about that. So the z-score is the name that is going to be applied to the position in terms of how many standard deviations we are away from the mean. So this is sort of a definition. If x is an observation from a distribution that has a known mean and standard deviation, and what's hidden behind here that you can see on your piece of paper, it says the standardized value of x. So this is going to be the standardized value. I'm abbreviating that. And it is called a z-score. So often the standardized value is called a z-score. Okay, goodness. Z-score. And it is calculated by taking whatever your value of interest is, what your observed value in the distribution, and you'd find the difference from the mean, like how far away is it from the mean, and then you divide that by the distribution standard deviation. So what you're doing is you're basically comparing it to the mean and dividing it by the standard deviation, and that'll tell you exactly how many deviations that observed value is from the mean. So it'll give you the position in terms of number of deviations or standardized deviations from the mean. This is the generic formula where x is your observed value, and this is the notation for mean and standard deviation. Not only does it tell you how far away in number of standard deviations and how many of these you are away from the mean, but it also tells you what direction. If you have a positive z-score, you have gone to the right of the mean, and if you have a negative z-score, you are to the left of the mean. So we're going to do a couple examples of finding z-scores, and then the next lesson will be on what you can do with those z-scores. So it's kind of piecing things together. What the heck does the normal distribution look like? Then this is how you find places and locations in the normal distribution. And then we'll finish with next class with how you use those values to help you. So this is just a bunch of output from a computer program, a stats program called Minitab. Population size is 25, and this is just like what your calculator would give you if you did one variable stats. So if we only are interested in a couple of values here. One, the mean is 80. This is our standard deviation. And again, with IB, we assume that's the population standard deviation. And with AP stats, that might change a little bit as you go into that. But for us, there's our mean and there's our standard deviation. And we have, these are test scores. Some individuals scored 86. That's the individual's test score. So that's our X. This is going to count as our mu, and this is going to count as our sigma in our formula. And if I want to know her standardized test score, it's going to take her 86, and then it's going to just tell me how many deviations above or below the average she is. So that formula was right up here. I'm just going to basically use this, and I'm going to fill in these numbers. So her standardized score, which is Z, is 86. It's always the score you're interested in first minus the mean. So this is always the value you're interested in. It goes first. Divided by a standard deviation of 6.07. And so I can do this calculation. That's 6 over 6.07, decimal right there, which means that's pretty close to 1. It's not quite 1. She is 0.988. So she is almost 1 deviation above average for her test score. Her score of 86 is almost 1 deviation better than, 1 standard deviation better than the whole class. Now we have another student. He got a 72. So to find his z-score, which is the same as asking for a standardized score, we take his score, value of interest, minus the mean, which was 80, and divide by the standard deviation, which is 6.07. So notice that you have to make this calculation on the top before you divide, otherwise you're going to get a wrong answer. So that's -8, which tells me that this individual score is below average, which it is because the average was 80 and that's less than it. And again, if I were to divide this in my calculator, I believe I get -1.32. So she's almost a deviation better than average. He is more than a deviation below average. He's closer to 1.5 deviations below average. And that's kind of puts their scores in easier terms to think about in terms of above or below in the standardized value. So this same individual, Jenny, has got an 83 on her physics test. She was not happy with that score. But then the teacher just told her the distribution was symmetric with a mean of 76 and a standard deviation of 4. And so this is a question that a lot of times they like to ask you, which test did she perform better relative to her class? So just if I looked at 86 and 83, I'd be like, well, she did better on this math test than she did on her physics test. But in relation to the rest of her class, I don't know. So I have to take her score and I'm going to standardize it. 83 minus 76 over 4. So again, her score minus the mean divided by standard deviation. 83 minus 76 is 7. 7 divided by 4 is 1.75. So she is almost 2 deviations above average for her physics score. She's not quite a deviation above average with her math score. So even though this is a better score, if you just look at the numbers, in relation to her class, this 83 is a much better, so she did much better in physics compared to the rest of her class. All right, you have something similar to try right here. This is heights. Again, I know that this notation is kind of the sample notation instead of population, but this is your mean and this is your standard deviation. So use that as your mu. We'll pretend like that's mu for now, and we'll pretend like that's sigma. And we've got Brent, and give this thing a pause and see what you get. Hopefully you've unpaused. That's what you should have gotten for a score. A z-score, he is over 1.5 deviations above average in relation to his class. He's pretty tall. He's almost 2 deviations above average from his class. All right, number 2 is a little bit trickier, so I want you to pause it and try number 2. You're going to have to use this formula, but you're going to be solving for the standard deviation. So pause it and give it a try. Please unpause it. This is our formula. This time I gave you his z-score for this new distribution, so that goes right in place of z. This is the new mean of a different distribution. This is this basketball team, not his class. So the basketball team is taller on average than his class. That makes sense. So this 76 is the new mean for the distribution. His height is still 74. I'm still interested in Brent. He's still 74. So this is going to force you to solve backwards for sigma. So your value for sigma should have been -2 over -0.85, and that should have been 2.35. So his standard deviation should have been 2.35 inches for the distribution of basketball teams. So again, first off, a couple things to note. He's actually shorter than average on his basketball team, where he is much taller than average in his class. The spread of heights in the class is pretty spread out. On average, kids are 4 inches apart from each other. The basketball team, they're much closer together. They're only just over 2 inches difference on average from this 76. So they're much closer to height. They're much closer to this average height on the team than the class is to this average height of 67. All right, I believe that's it for calculating z-scores. So now you kind of know about how to find a position anywhere in a normal distribution. It's this formula right here, and it basically just tells you where you fall along this realm. If it's not exactly 1, 2, 3, etc., it could be any position along there away from the mean of 0. All right, enjoy.